No, it's my... Ah, damn it, I just burped into the microphone. I thought I was muted. Hey, you guys. How's it going? Am I... No, you should... I meant to leave this screen up when I was not here yet. So you would know I'm not here yet. But I'm here now. It's 142 day 2. We were talking about the product rule. Do you guys have any homework questions before I go? No one said anything in the text. So... I guess not. Let's see. We did... Do I have that open? What's the last thing we did? We did... Yeah, we did one where you have to do parts twice. Basically that one. Okay. Let's talk a little bit about the philosophy of integrating by parts. There's this... when you integrate by parts... my stylus is dead. If I hold the button, will it wake up? It's hard dead. This thing's only lasting half an hour now. All right. So before I get into the philosophy of integrating by parts, let me do another basic example. Let's say we want to do the integral of x natural log x. We just did a bunch of examples where we said x is a really good choice to make for u. I will need to pick a u, and then after I pick my u, my dv is automatically going to be everything else. And for my last couple examples, u equals x seems like a pretty good choice for a u. If u is x, then du is dx. The x goes away. That's good to make a thing go away. The new integral will be simpler if there's not a u anymore. If u is x, then the integral by parts is that integral u dv equals uv minus integral v du. If u is x, then dv must be everything else in the integral, so that's natural log x dx. So v is going to be, what's the antiderivative of natural log x? Oh crap, I don't know the antiderivative of natural log x. If you said it's 1 over x, it's not. That's the derivative of 1 over x. That derivative is what you do to go from u to du. We need an antiderivative to go from dv to v. And the fact that we can't find a v means this integral by parts broke immediately, which is the best time. If something's not going to work, you want to find out immediately that it doesn't work, so that's kind of not so bad. Well, I'm still lecturing about integral by parts, so an integral by parts is probably a good idea to do here. If making u be the x wasn't a good idea, maybe I should let u be the other thing there. Try u as natural log x. If u is natural log x, then du will be... What's the derivative of natural log x? Derivative of natural log x is 1 over x dx. If dv is everything else, the natural log is taken, we still need x and dx to get used up, so that'll be dv is x dx. What's v gonna be? V is an antiderivative of x, half x squared. I can put a plus c, I usually don't want to, I'm not going to unless I see a good reason. I don't have one here. There we go. Cool. So the integral by parts formula says that this integral equals uv, that's natural log x times 1/2 x squared, minus the integral of v du. V du is half x squared times 1 over x dx. A lot of people will go from this to equals 1/2 x squared natural log x minus, they get excited because I know the integral of this. The integral of half x squared is 1/6 x cubed, times I know the integral of this. The integral of 1 over x is natural log absolute value x. And this is wrong. Remember, the product rule is like a whole rule. For plus and minus, there's no plus rule and no minus rule, because the derivative of f plus g is just f prime plus g prime, right? But products are messy. We had to have a whole section or two about the product rule, because to take a derivative of a product, you don't just take the derivative of one times the derivative of the other. If it doesn't work for derivatives, it can't work for integrals either. People really get tempted to do a thing that you can't do right after integration by parts. I don't know why that's the most tempting time. I guess the rhythm of an integral by parts is now we should do this integral. But you need to inspect the integral and figure out how to do that integral. In this case, we're able to do the integral because x squared times 1 over x combines into one thing. I can't integrate them separately, but I can smush them together, and I am able to smush them together because they're both powers of x. What is this? This is 1/2. The 1/2 can come outside. Integral of what is x squared times 1 over x? X squared over x is x. I need to integrate x, and I can. I get half x squared natural log x minus the integral of x is half x squared, with that half makes 1/4 x squared. There's our derivative. I think it's a good idea to take the derivative of this to check your work. Not just about checking your work, but about taking the derivatives of these things that you do by parts makes integral by parts a thing that you get in your guts. You're going to find after you do a dozen homework problems that when you are making mistakes, they're often just off by a minus sign or off by a constant. And if you've taken the derivatives of these things and seen how they're supposed to cancel out, you might be able to fix that constant or fix that minus sign real quick without... that can be a useful thing to do. I don't have time to, or I'm not going to do it right now because I want to get through more examples, but take derivatives of these things in the homework. It's great. So, what happened in this problem? Using u equal x wasn't great. Using u equals natural log x was great. The moral of the story is u equals natural log x is super great, because the derivative of natural log x has no natural logs in it anymore. It's very rare that you know the integral of natural log of something right away off the top of your head. So you need something to make the natural logs go away, and parts is the thing that does that. Derivative of natural log is no longer natural log. Derivative of an exponential is still an exponential. Derivative of a trig is still a trig. Derivative of a power of x is still a power of x. Natural log is nice because it stops being a natural log when you take its derivative. Similar thing for inverse trig functions. Inverse trigs, natural logs are great candidates for, if you see an integral that has an inverse trig or a natural log, you probably need to do parts, and in particular make that the u. When I was an undergrad, there was a rule of thumb acronym thing called LIATE. I don't know if this is valuable. I'm going to show it to you because someone showed it to me. The main thing is, here's what this LIATE is saying. These are 5 different types of functions. Logs, inverse trigs. A is for algebraic. That's usually x to a power. Maybe a square root of x, maybe a power of x, maybe just a polynomial. T is for trig. E is for exponential. And the order that we put them in, this is written like this to say that when you are trying parts, a good first choice is let u be the thing that is to the left in this list, let dv be the thing that is to the right in this list. And I think the valuable part is log and inverse trig go first. Make those the u if they are there. The rest of this is just whatever. But this is a thing I saw. Maybe this is something like if you have a trig and an exponential, it doesn't really matter, but take your choice. Trig and exponential are good things to be on the far right because they're easy to integrate. I guess it depends on the trig function. And if you look at the rules we've been following, when we did x times sine x, this was the x and this was the sine x, and we used that as the u, and that was good. When we had x times natural log x, well, natural log's on the other side, use that as the u. He wins out on that argument of who's going to be the u. Anyway, this is just a rule of thumb. If you don't know which way to go, this Lyautey thing can be a first thing to try. I don't think this is a super smart rule, but it's just a rule. It's not a rule. It's a suggestion. It is not a bad suggestion. Let's try. Okay, let's try a fun one. God, I love this problem. We're gonna integrate e to the 2x cosine 3x. What have I got here? Let's say I just wrote down this Lyautey thing, and I love doing this. Trig is left of exponential. Here it doesn't actually matter, but if I'm looking for a thing to try, let's try making u the trig part. Let's make dv the exponential part. U is going to be cosine 3x. dv is going to be everything else is going to be e to the 2x dx. If u is cosine 3x, then du is the derivative of cosine 3x. Derivative of cosine is negative sine, leave the inside alone, times derivative of the inside. V is going to be the integral of that. What's the integral of e to the 2x? Integral of e to the x would be e to the x. The constant means I got to divide by that constant. This is the baby substitution that I want you to be able to do in your head, because you want to be able to do it right now in the middle of this integral by parts. If you don't like doing this substitution in your head, the thing to do is to do the u substitution, u equals 2x at the very start, and that'll shift the entire integral a little bit, but now this part will be an easier integral to do. I don't think it's worth it to do that extra substitution. There'll be times when you have to do a substitution and a parts in the same problem. This isn't one of those times, and I'd rather, if you can do it easy, do it easy. Like, just get the hang of dividing by that 2. And the important thing is 2 is a constant, is why you're allowed to do this. And if you're not clear, double check. What's the derivative of v? Derivative of this is 1/2. E to the something, leave it alone, multiply by the derivative of the inside, the 2 and the 1/2 cancel. Yes, e to the 2x is correct. You should have left Cal 1 really good at looking at functions and writing down their derivatives, which is kind of nice because it means every integral you do in Cal 2, it's easy to check your answers. That is not always the case, but yeah, let's do this problem. Integral by parts formula says integral of u dv is uv minus integral v du. So this integral equals uv is cosine 3x times 1/2 e to the 2x minus the integral of v du is 1/2 e to the 2x cosine 3x. Here's a question to ask yourself is, have I made the problem any easier? We used to need to know how to do the integral of e to the 2x cosine 3x. Now we need to know how to do integral of e to the 2x. Wait, what? I did this. Oh, I screwed this up. Oh, that's u. That's not du. Dang it. Sorry. Minus the integral of v, 1/2 e to the 2x, du is -3 sine 3x. So this, if I clean it up a little, is 1/2 e to the 2x cosine 3x minus negative Integral of 1/2 times 3 is 3/2. I'm going to leave that inside the integral sign. Because soon I'm going to stop writing this, and I want this integral to be self-contained. I want just blah plus without having to deal with a constant out front. Come on, stylus. I got real stylus problems. Today and every day. Okay, we used to need to know how to do what's the integral of e to the 2x times cosine 3x. Now we need to know how to do the integral of e to the 2x times sine 3x. Has the problem gotten any easier? No, sine and cosine in like any reasonable metric are the exact same difficulty level of a complicatedness of a problem. So the problem's not any easier. We're going to keep going anyway. Like it's a pretty reasonable thing to say, I'm going to stop and go try something else once you see that doing parts didn't make the problem easier. It turns out it's worth continuing. What should we do now? Well, I saw the last one I tried an integral by parts, so I'm going to try an integral by parts again. I'm going to make a mistake right now. If there's a reason that it's worth putting t before e in Lyautey, it is that to remind you to do the same thing every time. Like if you make u the trig and dv the exponential, then you should keep making u the trig and dv the exponential. And this isn't just for trig exponential. Whenever you do integration by parts twice in a row, you really want to make sure you keep going in the same direction. This cosine and then sine was the u thing. I want to make that continue being the u thing. If dv was the exponential thing, I want to make dv continue to be the exponential thing. I'm going to not do that first because I want you to see what goes wrong when you mess this up. It's a weird specific thing that'll happen, and when it happens to you, I want you to be ready for it. So I'm going to make the mistake and let u be, I'm going to switch it over and let u be the exponential part. Let's let u be 3/2 e to the 2x. The 3/2 has to go somewhere. I'm sticking it on here. I could pull it outside the integral, but I don't want constants outside the integral because I want to be able to write blah 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 plus and not have anything outside the plus. U is this. du is, what's the derivative of this? 3 e to the 2x dx. The 2 comes out, gets multiplied by the 3/2, so you end up with just 3. What's dv? If u is 3/2 e to the 2x, dv must be everything else. dv is going to be sine 3x. v is the integral of sine 3x. Integral of sine is negative cosine. And I got to divide by 3. So dv is sine 3x dx. v is negative 1/3 cosine 3x. I got that this thing equals 1/2 e to the 2x cosine 3x plus... Now I need uv minus integral v du. What's u times v? It's 3/2 e to the 2x times negative 1/3 cosine 3x. Now minus the integral of v du is negative 1/3 cosine 3x times 3 e to the 2x dx. So, what is my new integral? I get 1/2 e to the 2x cosine 3x plus the 3 and the 3 cancel. I get negative 1/2 e to the 2x cosine 3x minus minus makes plus, the 1/3 and the 3 cancel, integral of e to the 2x cosine 3x dx. Well, earlier I was thinking about difficulty, and I said that that first integral by parts didn't look like it was going to be useful because e to the 2x cosine 3x looks like it's the same difficulty as e to the 2x sine 3x. Now it's even beyond them being the same difficulty. E to the 2x cosine 3x is the exact same integral as e to the 2x cosine 3x. And hey, wait a minute, this thing and this thing are opposites, they cancel each other out. I just got that this integral equals itself. Well, I already knew that this integral equaled itself. So, that sucks. This is like... I was in 4th grade and I was into magic, and some relative got me a book of magic tricks, and I was really frustrated that half the magic tricks in this book are about tying knots in ropes. And there's like these magician's knots where you tie this knot in a rope and then you tie this knot in a rope, and the two knots untie themselves. And that's what's kind of going on here. This is how I think about this: is the integral by parts turned the integral into something else, and then switching streams, switching the role of the u and the dv, turned the new integral back into the old integral in a completely useless way. I got that the integral equaled itself. The thing you're doing when you have the original u and dv, and your new integral is going to be v and du, so something got derivatived and something got integraled. And if you switch them, well, now the integral gets derivatived, and the derivative gets integraled, and I have this times this, which is the exact original function. Here they're a little bit off because where the constants are got shifted, but that doesn't really matter. I am learning that the integral equals itself, which means I'm learning nothing. The integral already equaled itself. This is what happens. Very often, if you do parts twice in a row, this can happen where you get the exact original integral and it's useless. Okay, so this is the wrong direction to go. Our problem was not that we did integral by parts. The mistake we made was switching streams. The u and the dv switched places between the first parts and the second parts, and that's always going to lead you with nothing useful. Instead, let's go back to this section, back to this line. Now let's go clear 1, clear x here, none of that was useful. Let's go back to edit, paste. Let's go back to this step. Our original integral, what was our original integral? It was integral e to the 2x cosine 3x. We learned that it was this, and I want to do parts again, and I've learned my lesson. I'm going to use u is the same thing that it was before. It's not quite the same thing because it got derivative. I had u was cosine. Now I'm going to use u as the sine thing. I'm going to let u be... I got some hiccups. I'm going to let u be the sine thing this time. Let's make u... I'll put the 3 halves on it. 3 halves. Sine 3x. dv is the other part, is e to the 2x dx. Again, I want the constant to be inside the integral. I guess I can show you. I keep saying this, and I don't feel like I'm explaining very clearly. The reason I want the constant inside the integral when I'm about to do parts again is if it's not, if I had the 3 halves outside the integral by parts formula, then it would have to be multiplied onto the uv minus integral v du. And I don't want to add an extra step where I distribute a constant in. It's easier to leave the constant in and the u can hold on to it just fine. Like writing 3 halves a couple times here is way easier than adding a whole nother line of work just to distribute it in. It's not a deep smart thing, it's just a small trick that to do a little bit less writing. If u is 3 halves sine 3x, then what's du? Du is the derivative of that. Derivative of 3 halves sine 3x is cosine 3x multiplied by 3. I get 9 halves. What's v? V's the integral of that. Integral of e to the 2x is half e to the 2x. This one's supposed to have a dx on it. So I get that this thing equals 1 half e to the 2x cosine 3x plus uv. 3 halves times 1 half is 3/4 e to the 2x sine 3x. I think it's prettier to put the e to the before the trig. Minus the integral of v du. V du is 1 half times 9 halves makes 9/4. I can pull that out of the integral. E to the 2x cosine 3x dx. And now I start to say, God damn it, this is the exact same original integral I had again. I got another useless line. But wait, this one wasn't useless. The old one was useless because I learned that the integral equaled itself, and I already knew that the integral equaled itself. This time, I'm learning that the integral equals some junk that doesn't all cancel away, minus 9/4 of itself. Well, how is that helpful? Like, I still need to do that integral. Wait. When you learn that something equals 5 minus 9/4 of itself, this is an equation about A that you can solve. We're going to do this goofy, ridiculous thing where I move the original integral to the other side of the equation and combine like terms and get, like I can solve for the integral. When I learned a fact about the integral in terms of the integral, as long as that fact isn't completely useless, like it equals itself, I can turn that into an equation that I solve for the integral. The traditional thing is you name the integral I. We say let I. Ugh, come on, stylus. I'm right at the good part. Damn it. Come on. We let I be the original integral. And we've just learned that I equals 1/2 e to the 2x cosine 3x plus 3/4 e to the 2x sine 3x minus 9/4 of the original integral. I want to add 9/4 I to both sides. 1 plus 9/4 is 13/4. I can do this. 13/4 of the original integral that I wanted equals 1/2 e to the 2x cosine 3x plus 3/4 e to the 2x sine 3x. To get I by itself, I need to divide by 13/4. I guess I'm going to multiply by 4 over 13. Cancel. I get that the original integral, the answer to my question is, what's 4 over 13 times 1/2? That's 2 over 13 e to the 2x cosine 3x plus 3 over 4 times 4 over 13 is 3 over 13 e to the 2x sine 3x. And you have to put the plus c yourself. I guess technically the plus c should have appeared when we combined these two integrals. These two integrals equal each other up to a plus a constant, so there's a weird, how come there's no plus c? You just either remember it yourself or it should have shown up in this goofy step. And this is it. This is a really weird integration technique. Like learning, usually I want the problem to get easier. If the problem stays the exact same, that can be useful. It's weird that this example shows off how getting the original integral can be useless or it can be the end of this problem. It sort of depends on whether you get exactly itself or something about itself. This is one where I'm definitely going to take the derivative and see what's going on. Check. We're going to check this out by taking the derivative. How do I take the derivative of this? It's a product. I need to use the product rule. Derivative of 2/13 e to the 2x is going to be 4 over 13 e to the 2x times, leave the second part alone, plus leave the first part alone, 2 over 13 e to the 2x times the derivative of cosine 3x is negative sine 3x times 3. Cool. Plus, this is also a product, needs the product rule. Derivative of the first, derivative of 3/13 e to the 2x is going to be 6 over 13 e to the 2x times, leave the second part alone, sine 3x, plus, leave the first part alone, 3 over 13 e to the 2x times, what's the derivative of sine 3x? It's cosine 3x times 3. This is supposed to simplify? It does simplify. Here is negative 6 over 13 e to the 2x sine 3x. Here's positive 6 over 13 e to the 2x sine 3x. Those cancel out. Here I have 4 over 13 e to the 2x cosine 3x. Here I have 9 over 13 e to the 2x cosine 3x. 4 over 13 plus 9 over 13 of something makes 13 over 13. E to the 2x cosine 3x. Sure enough, that's what it was supposed to be. We were integrating e to the 2x cosine 3x. This is a weird trick. Integrating by parts until you get the original problem can happen in a good way and it can happen in a bad way, and it's weird. Cool. Let's try something else. I like this one. Let's do the integral of sine inverse of x. Why am I doing this in integral by parts? The integral by parts is for when you have something times something. Like, why would... This is only one thing. How do I pick a u when there's no other thing to be a dv? I guess the moral of the story, maybe Lyautey is telling us this, is inverse trig loves being the u in an integral by parts, and so does log, so much that do integral by parts even if there's only one thing. There's no chance of integrating sine inverse with the stuff we have, but I do know how to take the derivative of sine inverse. Hey, if you don't know the derivative of sine inverse, you should go learn that. U is gonna be sine inverse x. dv is gonna be everything else, and now everything else is just dx. Okay, that's not too bad. If u is sine inverse x, then what's du gonna be? Don't mind the pause while I Google the derivative of sine inverse x. Yeah, that's what I thought it was. Wait. Yeah, cosine is the one with the negative. Sine does not have the negative. That's the thing I mess up. du is the derivative of sine inverse is 1 over root 1 minus x squared dx. V is going to be the integral of dx. How do I integrate nothing? If it helps, you can call that dv is 1 dx. What's the integral of 1? Oh, that's right, v is x. It's also, if dv is dx, it's sort of easy to say, letting v be and x be the same thing will make dv and dx be the same thing. Like, it's, these two lines are saying so little that it hurts my head sometimes. So, the integral is going to be uv minus integral v du. That's going to be u times v is x sine inverse x minus the integral of v du, x over root 1 minus x squared dx. So I've turned that integral into this integral. Is that helpful? Yeah, definitely. It used to be something with a sine inverse, and now there's no sine inverses anymore. Maybe I don't know how to do this immediately, but I know there's stuff there I can mess with. It's not just one big block that I don't know how to do anything with. So, what do? Ideas? Man, it's really good to have a room full of students to say, what do you want to try? Because I want to do some wrong things sometime, but I feel dumb just saying, hey, I'm going to do the wrong thing now. I guess it's more fun to take a student's suggestion and run with it, as if it's a great suggestion, even when I know it's not. Because that's what you got to do in calculus. You try stuff. We do a substitution. U equals 1 minus x squared is a good choice. It is a thing I see on the inside, whose derivative of 1 minus x squared is negative 2x. Well, I don't see the negative 2, but I do see an x, and that's the important part. The constant fixes itself. Du, come on. Du is negative 2x dx. I wish I had a negative 2 here. Well, I can put the negative by canceling it from there. Multiply by 2, divide by 2, there we go. So now this substitution will go down smooth as butter. Equals stuff plus 1/2 integral of, that becomes square root u on bottom, negative 2x dx all becomes du. I'm integrating 1 over square root u. This is a power rule problem. This is the integral of u to the negative 1/2. The integral of u to the negative 1/2 becomes u to the positive 1/2. Divide by a half. Well, hey, there's a 1/2 out there to cancel that one. It's just that plus c equals. So our answer is x sine inverse x plus the square root of 1 minus x squared plus c. There we go. Yeah, sometimes you do parts even if there's only one thing. Oh, let's do this one. Does this work? Let's do the integral of natural log of x plus 6. Again, just like the last one, there's only one thing here, but log loves integrating by parts so much that it's a good idea even when you only have the one thing. We're going to let u be natural log x plus 6. du is going to be the derivative of that. dv is everything else in the integral, that's only dx, so v is x. du is derivative of log x plus 6 is 1 over x plus 6 times derivative of the inside is just 1 dx. Integral by parts says this is going to be uv minus integral v du. Yeah, so that's u times v is x times natural log x plus 6. Come on. X times natural log x plus 6 minus the integral of v x times du is 1 over x plus 6 dx. The thing I want to show off with this problem is I can notice x times 1 over x plus 6, I guess the time I should have noticed it here, is when I made vx, I had the option of putting a plus c here. And I want to look ahead to the fact that I'm going to have to integrate this thing times this thing. And instead of multiplying 1 over x plus 6 by x, life is way easier if I multiply 1 over x plus 6 by x plus 6. This problem is an example of a time that it can be a good idea to put a plus c on your v. If v was x plus 6, that means that v du becomes a super easier integral. Integrating x times 1 over x plus 6 doesn't look that hard, but you know, it's not for free. As opposed to if I put an x plus 6 there, it becomes a completely for free integral. The thing you got to keep in mind, if you go back and change what your v was, you used v over here also, so you got to fix that copy of the v also. I get this becomes minus the integral of 1, so that becomes minus x. Our answer is I gotta change the battery on the stylus, I guess. I had a revelation last week that if I double tap the button on the butt of the stylus, it wakes it up sometimes. I have x plus 6 natural log x plus 6 minus x plus a constant. There's our answer. Hooray! Once in a while, a student will be excited about, oh, I gotta remember this absolute value. We don't put an absolute value here because at no point did we integrate 1 over x. The absolute value shows up when you integrate 1 over x. We only took a derivative of the natural log they gave us, so there's no reason for us to change the absolute, to add an absolute value. If I do add an absolute value, I'm just changing this function so it's defined more times. So I'm not adding any wrong answer, but I'm adding a bunch of solution that's not actually solution. You want to get to a position where you do enough integration by parts problems that the integral of x e to the 2x, you want to know, hey, parts is going to work right away. If I make that u and I make that dv, the x will be gone. It'll be an integral of just e to the with some constant. I know how to do that. You want to do enough integration by parts problems that you look at this and say, I know that integration by parts will work on this. A problem similar to the one we did last time, integral of x cubed e to the 5x. This is similarly there, except I have to take the derivative 3 times for it to go away. And I can integrate this 3 times. It's not going to be pretty, but I can do it. Like I'm just going to divide by 5 every time I do. There's going to be some other constants coming off the x squared. So parts 3 times, you want to be good, have done enough problems that you know right away parts 3 times works. But usually you don't want to have to write out integrating by parts 3 times. So there's a trick for doing multiple parts all in a row without that much writing, and it's called tabular integration. And the people write this in different ways, but if I wanted to integrate x cubed e to the 5x dx, the usual way, or the way I've seen it written, is you start with the thing you're going to differentiate, your u choice here, that's going to be your u choice over and over. You put your dv thing here, because this is kind of a u type thing and a kind of a dv type thing, because these aren't, we're not exactly doing integration by parts right now. This is basically just a shorthand for doing parts a bunch of times without all the writing. You differentiate one side. You take the derivative till you get 0. And then you integrate the other side. What's the derivative of x cubed? It's 3x squared. What's the derivative of that? 6x. What's the derivative of that? 6. What's the derivative of that? 0. Keep going till you get the 0. Because that's the thing that's telling you how far you have to do the other column. Do the derivative side first, and you want something that's going to eventually be 0, which means you want a polynomial to do this tabular integration thing. After derivativing one side, differentiate is the word there, differentiating the one side, you integrate the other side. Integral of e to the 5x is 1/5 e to the 5x. Integral of that is 1/25 e to the 5x. Integral of that is 1/125 e to the 5x. Integral of that is 1/625 e to the 5x. After you've got this, your answer is going to be this product, and this product, and this product, and this product. And one of them is positive, negative, positive, negative. I can write down my answer now. Oh my god. I can write down... I can write down my answer. My answer is the integral of x cubed e to the 5x looks like it's x cubed times 1/5 e to the 5x. This was a positive one. Minus 3/25 x squared e to the 5x. Plus, this times this is 6/125 x e to the 5x. Minus this one is 6/625 e to the 5x plus a constant. That's tabular integration. There's nothing deep going on here. If you like do the integral by parts a couple times, you'll see how the u and the dv become whatever they become. There's smart ways of doing this that where you don't have to end up with a 0, where you can write minus the last thing as you need to do this last integral, however you do that. I never learned that, so I'm not going to make you learn that, but that's a thing you can do. What am I? Oh, that's what that is. Let's try. Ooh, that's a good example. Let's do the integral of... Ah, man. X tangent inverse x. I want a u, I want a dv. I see an inverse trig function. I always want u to be the inverse trig function. I guess maybe unless there's a log there. If you have both a log and an inverse trig, you're probably in big trouble. U is inverse trig, dv is going to be everything else is x dx. So du is going to be, what's the derivative of tangent inverse? It's 1 over x squared plus 1. That's the easy one. V is going to be the integral of that is half x squared. I can put plus a constant. Do I want to put plus a constant? Oh, wait a minute. This is the same type of deal I was in before, where this fraction, instead of 1 over x squared plus 1, I'd love to be multiplying by x squared plus 1 so things cancel. I have the 1/2 messing me up. I can put plus a half, and now that's half of x squared plus 1. This product won't be a fraction anymore. Awesome. This is a great excuse to do that trick. I get equals uv is half x squared plus a half times tangent inverse x. I'm writing it as vu because I like putting the pretty part first. Minus the integral of v du is half x squared plus a half times 1 over x squared plus 1. Factor out that 1/2. You're left with just a half. The integral of half a half is x over 2. Boom. Can you do it without noticing that putting a plus a half here is cute? You can. This is like the cutest possible solution. There's no... Don't walk away from this lecture thinking that this is the correct way to do this. These problems have a million ways to do them. Coming up with your own way that works is great. This is the fun of teaching this class and saying, hey student, what's your idea? And trying that idea out, because there's a good chance like bad ideas work too. And like I shouldn't have just said bad idea right then. Like the point is they're not bad ideas. Anything else I want to say about parts? Oh, yeah, I have a triple I want to do. Let's try the integral of x natural log x e to the x. Sometimes there's these triple integrals that I have like no idea what to do. Let me double check that's not a homework question. Do I still have the homework open here? Nope. Homework. I have x sine cosine, not one of these. What do you do with this? Triple products are weird, and I don't have a really good intuition other than try stuff and see what works. If I make u log x, or Then dv is everything else. dv will be x e to the x dx, which makes v is the integral of that. I can do the integral of that, but this is going to be parts again. And I don't really want to do a parts problem in the middle of my parts problem. I might try that as a last resort, but for now that seems like way overkill. Instead, let's try u equals, maybe this is a better idea, u equals x log x, and dv is just e to the x. Does this work? Often I find myself stuck making two of the things the u because I can take a derivative of two things. That's the product rule. I don't need a special trick for that. Derivative of x log x is derivative of the first, leave the second alone, plus leave the first alone, derivative of the second. V is the integral of this is e to the x. This is natural log x plus 1 dx. Okay, so I want uv minus the integral of v du. What is that? uv is x log x e to the x minus the integral of v du. That's natural log x plus 1 times e to the x dx. Should I split this up into two? I can write that as log x e to the x plus e to the x. Pull this one out because I know how to do that integral. I'm still left wondering how to do that. That doesn't seem actually that productive because when I take the derivative of log x plus 1, this is a thing I can take the derivative of right now, and it's just as simple. Like, derivative of log x plus 1 isn't any messier. I think I'm going to be doing parts with this is the u, and this is the dv. Let's make u equal log x plus 1. dv is e to the x. du is 1 over x dx. v is the integral of that is e to the x. So I get equals x log x e to the x minus... Oh, I left the minus outside the integral. This is the thing I hate. Okay, minus uv is e to the x natural log x plus 1 minus the integral of v e to the x du 1 over x e to the x dx. And let's distribute that minus in by making that a minus and that a plus. And integral of e to the x over x. Do I know how to do that? It certainly seems easier than the original problem. Now, how do I do this? Try a u substitution? Maybe I should let u equal 1 over x? It's not obviously a good idea, but it's not obviously a bad idea. Let's try that. I'm going to try the u substitution, u equals 1 over x. Ideally, I want u to be something I see on the inside whose derivative I see on the outside. This doesn't really have any of that. But I'm going to try it anyway. Derivative of 1 over x is negative 1 over x squared dx. This is one of those places where using this as the u isn't great. It might be nicer to write x equals 1 over u. So dx is negative 1 over u squared du. What does this become? Now this is the integral of 1 over x becomes u. X becomes 1 over u. Dx is negative 1 over u squared du. One of these u's cancels. I get integral of 1 over u e to the 1 over u. Ooh, with a negative sign. Ooh. That doesn't seem better. Well, I don't don't know how to do this. If you figure out how to do this integral, send me a message. I was wondering about this one earlier today when I was like thinking about what I'm going to lecture about. This is what I get for grabbing a problem that I don't know that I know how to do. So that'll be it for parts for now. Let's start talking about our next topic is trig tricks. Wait, what's our next topic? Trig tricks, then trig substitution. Why do I have? Oh, I think these notes might be out of order. Give me 1 second to see if this is, if I have the... Oh, no. Dang it. Okay. I'm going to need a minute to print off some notes. You know what? I'm just going to wing it. I'm not going to print anything off. I'm going without notes. You guys. I'm doing improv, jazz, math. You guys, this is amazing. The next section, trig tricks. Our main goal is to be pretty good at... There's like a bunch of individual little tricks that you want to know to be good at integrating trig stuff. And that's going to be what we're focused on today. There's a bunch of combinations of this. Let's see. One... Damn it, I can't do this without notes. I'll be right back. I'm going to go print off some notes. Hey guys, I'm back. And I remembered a thing I should have said from parts. Oh my god, this stupid stylus. I think it's gotta be the battery, because when I change it, it works for a few minutes. I hate this feeling like I'm changing the battery, and it's not definitely getting better. So maybe this is just me making myself feel better. But I think it does get better for a little bit when I change the stylus battery. Yep. Okay. Was there? I am not having fun with this. I can't write with my mouse. That is not a solution. Let's do an integral by parts that I should have done. Let's do, the thing I should have pointed out is how you deal with an integral by parts when it's definite. Let's do the integral from 0 to pi over 2 of x cosine x. This is not a particularly deep integral by parts. I know how to do this. I'm going to let u be the x and dv is everything else. This is one of these places where the x goes away and I can integrate cosine as many times as I need to. So dv is cosine x dx. Du is derivative of that is dx, is 1 dx. V is the integral of that is sine x dx. The question then is, what does the integral by parts formula become when there's bounds of integration? And the point I'm trying to get to is when you have bounds of integration here, those bounds of integration are here. What do you do with this? This part's already been integrated and you need to evaluate it from a to b. The a to b is still there on both parts of the right-hand side of an integral by parts. It's not like substitution where you need to change the bounds of integration. You just need to use the bounds of integration. For the part you've already integrated, that means you still need to plug in the numbers. For the part you haven't integrated, the bounds are still there ready for you. So the integral of x cosine x from 0 to pi over 2 is uv is x sine x evaluated from 0 to pi over 2 minus the integral of v du is sine x evaluated from 0 to pi over 2. What is this? This is pi over 2 sine pi over 2 minus 0 sine 0, which is 0 doubly, minus what's the integral of sine? It's negative cosine. Evaluate that from 0 to pi over 2. So this is, what is sine pi over 2? Sine pi over 2 is 1. So this is pi over 2. Plus what's cosine pi over 2? It's 0 minus cosine 0 is 1. So this is pi over 2 minus 1. That's what you do with bounds of integration when you're doing integrating by parts. Alright, let's do these trig tricks. Trig tricks is a dumb name for a section, but it's not like integration by parts. You learn one trick, one technique, and many ways to do it. For trig stuff, there's just a bunch of individual little dumb tricks to learn, and we're going to sort of throw them all at you. One, at the very least, we should know how to integrate every of one of the basic trig functions. Some of these are easy, some of these are less easy. Sine and cosine, we know this. Integral of sine is negative cosine. Integral of cosine is sine. Tangent. How do I do tangent? If I rewrite it as sine over cosine, I immediately see, hey, this is a good place for a substitution, because cosine is on bottom, it's kind of stuck inside, and the derivative of cosine is negative sine is basically sine, is outside on top with the dx. I do the u substitution, u equals cosine x, du is negative sine x dx, so negative negative, I get equals negative integral 1 over u du. That's negative integral not an integral anymore, negative natural log absolute value u plus c. It's negative natural log absolute value cosine x plus c. Integrating cotangent is the same trick the other way around. We could write it down and put a box around it. I don't think it's valuable memorizing these, or not these ones, because the substitution is real easy and fast. If you look at a chart, they will probably negative natural log something is natural log of 1 over that thing. So most integration tables will write this as natural log absolute value secant. Is a unnecessary simplification. I guess you're saving a tiny little bit of ink when you write it that way, but whatever. Secant and cosecant are the hard ones. What's the integral of secant? The trick, the trick is crazy. You can rewrite it as 1 over cosine. That is not that useful, is it? I don't think it's. No, it's definitely doable that way. The way I saw it, and the way I still remember it, is... Here, watch this. Let's multiply the top and bottom of secant by tangent. Now I'm in excellent position. I'm in the same place before, because I have tangent stuck on bottom, and the derivative of tangent is secant tangent. Wait, no, that's not right. The derivative of tangent is not secant tangent. The derivative of tangent is secant squared. That's not right. Let's try this. Let's multiply the top and bottom by secant. I'll have secant squared x on top and secant x on bottom. Here's another way of writing the integral of secant. And now I'm in a good shape because I have secant stuck on bottom, and I have the derivative of secant is secant squared stuck on top. Wait, no, that doesn't work right either. Derivative of secant is secant tangent, not secant squared. You have that guy as your derivative, and you have that guy as your derivative. What am I supposed to do? You combine these two tricks in this goofy way. I'm going to have secant x, and I'm going to multiply it by secant plus tangent over secant plus tangent. So this becomes the integral of secant squared x plus secant tangent x over secant plus tangent. Now, the bottom is secant plus tangent. The derivative of secant is secant tangent. The derivative of tangent is secant squared. Now the top is the derivative of the bottom. I had to use both with a plus. We can do the substitution. U equals secant plus tangent. Du is secant squared x plus secant tangent x. So this is the integral of 1 over u du is natural log absolute value u plus a constant. The integral of this is natural log absolute value secant x plus tangent x plus a constant. This is an amazing this is such a dumb trick. For me, this one was worth memorizing. I memorized this when I was an undergrad, although I still needed to learn. I never did memorize cosecant. Does the same trick, but use a cosecant and a cotangent, and there will be a minus sign, and it'll be a pain. There's another way to do this. I don't know if it's better or worse. I'll show it to you. I guess I'll show it to you for cosecant. If I think of this as 1 over sine, actually, you know what? Let me show you the other thing first. we're going to learn a bigger trick for which this is a small version. Let's learn the bigger trick first. If I have to integrate, so those are all the basic functions. There's some specific tricks for those. Say you want to integrate sine to the 7th of x, cosine to the 4th of x, dx. And in general, when you want to integrate sine to a power of x, cosine to a power of x, you have a bunch of sines and a bunch of cosines, all multiplied together. What do you want to do? And there's two versions. The good, easy version is if A or B is odd. You're hoping for an odd power of sine or cosine. That's the easy case. And we are in that case now. I have 7 sine x's. Why is it so good to have 7 sine x's? The good thing about an odd number, so this is the way I remember it, is when there's an odd number, you can pull one of them off. I'm going to pull one of those sine x's off and stick it by the dx. And when I stuck it by the dx, it gave me the idea, aha, I like having a sine x dx. If I went looking at that sine x dx makes me think about the substitution, u equals cosine x. Du will be negative sine x dx. The minus sign I don't care about. I just need to know, can I write everything in terms of cosine? Well, these are already a bunch of cosines. That's u to the 4th. But these sines are not cosines. But the good news is, I had an odd number of sines, now I have an even number of sines. That means this is something to do with sine squared. And an even number of sines is a power of sine squared is a thing I can turn into cosines. Because sine squared is 1 minus cosine squared. And now this substitution goes nicely. It turns into negative integral 1 minus u squared cubed times u to the 4th du. And you can get into places like, now you're staring at this and thinking, what goofy, cute substitution can I do there? And maybe there is a good one, but worst comes to worst, this thing is a polynomial. You can FOIL this out and integrate it. I need to cube 1 minus u squared, which isn't fun, but it's doable. What is 1 minus u squared cubed? It's, when I square it, I get 1 minus 2u squared plus u to the 4th times 1 minus u squared, and now the third one gives me 1 minus u squared minus 2u squared is minus 3u squared plus u to the 4th plus 2u to the 4th makes plus 3u to the 4th minus u to the 6th. This thing, after foiling out, which is not fun, but it's not the worst, 1 minus 3u squared plus 3u to the 4th minus u to the 6th times u to the 4th du. Don't get this close to the finish line and try to integrate this and integrate this. This is integrable because it is a polynomial. Just keep distributing until you can see how to use the power rule. I get equals. I'm going to push in the u to the 4th and the minus sign all at once. Minus 1 times u to the 4th is minus u to the 4th plus 3u to the 6 minus 3u to the 8 plus u to the 10. Now I'm ready to integrate. I get negative 1/5 u to the 5th plus 3/7 u to the 7th minus 3/9 is 1/3 u to the 9 plus 1/11 u to the 11 plus c, and u was cosine. So this is negative 1/5 cosine to the 5th x plus 3/7 cosine to the 7th x minus 1/3 cosine to the 9th x plus 1/11 cosine to the 11th x plus a constant. Ooh, gross. But, like I said, this was the easy case where one of the numbers was odd. If they're both even, you're going to have to do what's called a power reducing formula. The simplest version of this is how do you integrate sine squared? Or how do you integrate cosine squared x? The thing we're going to end up using is a trig identity. You may remember from your trig class there were 3 different versions of the double angle formula for cosine. The simple one was that cosine 2x is cosine squared x minus sine squared x. If you just use angle addition for x plus x, this is what you'll have written down. But you can rewrite this in different ways because cosine squared is 1 minus sine squared, so I can write that as 1 minus sine squared minus sine squared. Makes 1 minus 2 sine squared x. Or I can use only cosines by rewriting sine squared as 1 minus cosine squared, so that makes it 2 cosine squared x minus 1. And you wrote down all 3, even though you didn't use all 3 very often. I think the reason that you learned all 3 of these at the time was now these are ways to change cosine squared and sine squared into something that's not squared anymore. The fact that cosine 2x equals 2 cosine squared x minus 1 means you can add 1 to both sides and divide by 2 and rewrite cosine squared x equals 1 plus cosine 2x over 2. Similarly, sine squared x equals 1 minus sine 2x over 2. These are worth memorizing. These are... Oh, no, damn it, Andy. Don't write the wrong thing down and then put a box around it. It's 1 minus cosine 2x over 2. I don't know if this is really useful, but when I was an undergrad, I would imagine what cosine squared looks like, and that helped me remember the other half of the formula. Cosine squared... Cosine x looks like this. Right? When you square it, you're kind of folding it up and making it positive. This negative 1 is going to get squared and become positive 1. One squared is 1 also. 0 squared is 0, so we're doing... Why won't my stylus work? I'm just gonna cry. I don't know how I'm supposed to teach like this. Joop, 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 joop. Joop, 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 joop. When you imagine squaring cosine x, you can see, you do kind of end up with a wave with half the wavelength, which is what cosine 2x is. When I imagine cosine 2x, I'm taking the purple one and shrinking the wavelength by a half. So cosine 2x will be, instead of going down the whole time, that'll be a full cycle down and then up. This should line up with that, and then down and then up again. And it's up again at the top. So I see that this graph is the same shape as the green one up here, but it's going negative and the other one should be positive. How do I fix that? Well, adding 1 will slide it up, and then cutting it in half makes it not too tall anymore, and that's why I've got the +1 and the divided by 2, and that, I don't know, that helped me remember which is which on these formulas. I don't know if this is helpful to anyone else. You need to be able to write these formulas down when you need them, because they are just the most straightforward way of integrating even powers of x. To integrate cosine squared x, I'm rewriting it as this thing, which I know how to integrate really straightforwardly. This is the integral of 1 plus cosine 2x over 2. I'll split that into two fractions. The integral of a half is x over 2. The integral of cosine 2x is sine 2x. Divide that by 2. You get this. Integrating cosine squared or sine squared is pretty straightforward. You just use this identity. When you have bigger, grosser powers of x, if I had cosine squared, or if I am integrating cosine to the fourth, let me check which one's in the homework. The homework has you doing What? I didn't put any of these in the homework? Oh, I gotta add some of these to the homework. Maybe some of these turn into that if you do goofy stuff. I might need more homework problems. Integrating sine squared x, say cosine squared x. Well, let's just do sine to the fourth. This is, again, a version of sine to the a. I have some sines and I have some cosines. The b here is 0, is even. The a here is 4, is also even. I'm in the hard case where they're both even. If one of these was odd, I would be in the easy case where I can pull off a thing and do a u substitution that's way nicer than using the power reducing formula. This is called a power reducing formula because it changes two cosines into one cosine. We're not in that case. We gotta suck it up and use the power reducing formula. This is sine squared x squared. I look up my formula for sine squared x. It's 1 minus cosine 2x over 2 squared. I FOIL that out. I got 1/4. 1 minus 2 cosine 2x plus cosine squared 2x. I know how to integrate 1. I know how to integrate cosine 2x. How do I integrate cosine squared 2x? This is an even power of cosine. I gotta use the same formula again. The reason it's called a power reducing formula, like the idea of power reducing is it reduces it only one step, and you gotta keep reducing over and over. The formula was that cosine squared x is 1 plus cosine 2x over 2. It helps me sometimes to rewrite that as cosine squared of anything equals 1 plus cosine to that thing over 2. Here my anything is 2x. So this is 1/4 integral of 1 minus 2 cosine 2x plus cosine squared 2x is 1 plus cosine 2x is 4x over 2. This is a half, is a like term I can combine with that one. So I get 1/4 integral. You might as well combine the like terms before integrating. 1 plus a half is 3 halves, minus 2 cosine 2x, plus 1/2 cosine 4x. And now it feels dumb having the 1/4 outside when there's all these fractions inside. Dx. So I get 3/8 minus 1/2 cosine 2x plus 1/8 cosine 4x. Still need to integrate it. I get 3/8 x minus integral of cosine 2x will be sine 2x, gotta divide by 2, 1/4 sine 2x, plus integral of cosine 4x is going to be sine 4x, gotta divide by 4, 1 over 32 sine 4x. That's what to do with an even power of x. Okay, this is the even and odd powers of sine and cosine thing. I paused to go do that before coming back to integrate cosecant again, because that trick works on this. This I can look at and think of this as sine x to the -1, and -1 is an odd number, so that should be good news for my ability to integrate that. But I want to peel off one sine x to stick with the dx. Was the idea of the trick when there's an odd. So I'll pull off a sine x to stick with the dx. What do I get after I add a sine x here? I gotta divide by sine x, so I get sine squared x. This is the integral of 1 over sine squared x, sine x dx. Okay. This was not so bad because I want to do the substitution where u equals cosine x. Putting the sine x next to the dx was my reminder that I like the I like the substitution. Why don't you just work? I like the substitution u equals cosine x. du is going to be negative sine x dx. The negative I can deal with, but this needs to be cosines here. So it's going to be negative integral. Change that sine squared to 1 minus cosine squared. So now my new integral is negative integral 1 over 1 minus u squared du. This doesn't look that bad. It's not that bad, but you need to know partial fractions, which is going to be this thing we learn in 2 more sections. So we can come back and finish this problem this way, medium easily, in a couple more days. It really isn't that bad, though, so this might turn out to be, I don't know. I guess in trying to cover this, I'm realizing why they did the secant plus tangent trick is the thing you can do right away, as opposed to doing it like this. It involves so many other things. Anyway. Let's see. Very similar to these power of sine, power of cosine thing is power of secants, power of tangents. And similarly, there's an even-odd version thing here, and the thing that makes them easy or hard, the way I remember this is the integral of secant cubed is this classic example of a tricky integral. The calculus teacher I had for Cal 2, the second one, I flunked Cal 2 the first time, made a big deal that integral of secant cubed is a beautiful problem that he loved putting on tests because it involves so many good different tricks. So this particular one was stuck in my head as an example of a hard thing. So the hard version is when A is odd and B is even. I guess I gotta switch the battery again. So just like sine and cosine, it splits into 2 cases. There's an easy one and a hard one. I have written down in my head that integral of secant cubed is hard. The hard case is when A is odd and B is even. That's the hard version. If A is even or B is odd, that's the easy version of this case. Let's try one where A is even. If I have the integral of secant to the 4th x tangent, what's the hard thing for B? We'll make that one even too. Secant to the 4th x tangent squared x dx. Alright, if A is even, I can pull off a secant squared. Like, I like this even because I like 2. Secant squared I know is the derivative of something. Maybe I don't remember right away what it's a derivative of, but I have a second to remember while I pull it off. Secant squared x, yeah, that's the derivative of tangent. I like the substitution u equals tangent here. Is that going to be good? It'll be good if this is all tangents. Well, you're already tangents. And you can be tangent. That's right, there's a trig identity about secant squared and tangent squared. How does that go? Sine squared plus cosine squared is 1. Divide both sides by cosine squared. That's right, tangent squared plus 1 equals secant squared. Secant squared I can replace with tangent squared plus 1. So I can do the substitution. This becomes the integral of u squared plus 1 times u squared du, and FOIL out that polynomial, integrate it. I'm not going to finish this problem because it's super easy from here on out. Right? When a is even, you can pull out a secant squared. That doesn't work if a is 0. We'll come back to the case when a is 0. If b is odd, let's try integrating secant cubed x tangent cubed x. So now b is odd. I can pull out 1 tangent and 1 secant. Secant tangent is also the derivative of something. So that will lead itself to a substitution. I want to do the u equals secant x, because that's the thing whose derivative is secant tangent. I have a u squared. You're ready to go. You are not written in terms of u's of secants, but I can make you be. I have an even number of tangents left over. I can turn an even number of tangents into secants. Tangent squared is secant squared minus 1. I get the integral of u squared times u squared minus 1 du. Again, FOIL out the polynomial, it's not that bad. If this was a tangent to the 5th, then this would have been tangent to the 4th. This would have been secant squared minus 1 squared. It becomes harder to FOIL it out in that case, but it's still just a polynomial. FOILing it out is not that bad. There's a chance that maybe there's some cute substitution that lets you not have to FOIL it out. But these are not that rough in that case. The situation is the exact same for cosecant and cotangent for the same reasons. If you have an even number of cosecants or an odd number of cotangents, you can pull out a cosecant cotangent or pull out a cosecant squared. It's the derivative of something. The thing works the same way. You need to be able to pull out the co-version of the Pythagorean identity there. What do you do if neither of those things is the case? Let's do the integral of secant cubed. Pulling out a trick for a u substitution isn't going to work. The thing we're going to try instead is we're going to do parts. I want to split this off some so that I have something I know how to integrate. Like, the tricky thing for parts is I want you to be... Jesus. I want to pull out my u and my dv, and I need dv to be something I can integrate. Secant is a pain to integrate. I can do it, but it's natural log something something. I'm going to get something really bad. The thing that's an easy integral is secant squared x. So u will be secant x. If dv is secant squared x, the integral of secant squared is tangent. I can put a plus a constant, but I don't think there's a reason to here. The derivative of secant, there's a dx here. The derivative of secant is secant tangent. dx. So that integral equals uv secant x tangent x minus the integral of v du secant tangent times tangent, secant x tangent squared x dx. Okay. Bad news, I still have an odd number of secants and an even number of tangents. I'm still in the hard case. The thing we do here is tangents I know how to turn into secants. Tangent squared, what's the deal with this? I had it written down a second ago. Tangent squared is secant squared minus 1. Aha! Now I can distribute that in. I got equals secant x tangent x minus, I'll split it into two integrals, minus the integral of secant cubed x dx plus the integral of secant x dx. This one I can do. It was a pain, but it was doable. This, bad news, is the original integral, but good news, it's not just integral equals itself. This is the good version where I have the original integral, I can move that to the other side, and it's not part of the problem anymore. So 2 integral secant cubed x equals secant x tangent x plus integral of secant x. Do you remember what it is? This is one that I recommend memorizing. Natural log absolute value secant plus tangent. This is where you multiply the top and bottom by secant plus tangent. Plus a constant, divide both sides by 2, and that's the integral of secant cubed. You get it's half secant tangent plus half natural log that. Whew, that's rough. So that's the power of secants and tangents, the power of sines and cosines. That's a similar power of... oh, we didn't do one where we had just... I mentioned if a is even, you can pull out a secant squared. I didn't talk about what happens if a is 0, if I'm integrating just a power of tangent. That's supposed to be the easy case also. Let's try one of those. The integral of tangent, we already talked about. If I have just tangent squared, this is one that throws people off a lot. How do I integrate tangent squared? If you're not watching live, pause the video and try this. Like, there's a couple good things to try. I always want to stop talking for a second when I say pause the video, but the whole point of the pause the video is I can keep talking. This is one that you try and you just get so mad when you remember. Tangent squared is secant squared minus 1. Give me my stylus. I gotta teach. The integral of secant squared is tangent. Done. Integrating tangent squared is super easy. What if you have tangent cubed? An odd number of tangents, I'm supposed to be able to pull off a secant tangent, but there's no secant there to pull. An even number of secants, I'm supposed to pull off secant squared, but there's no secant squared there to pull. What do I do? Well, you just sort of try stuff out. I think the best thing to do is split off a secant squared, probably. Like when there's no secant squareds, I can change it so that there are, by rewriting that as tangent x times tangent squared, which I can write as secant squared x minus 1. I get integral secant squared x tangent x minus tangent x. This I know how to integrate. It's negative natural log cosine, or positive with that minus there. And the secant squared I can do by pulling off a secant times secant tangent. So For a small number of tangents, it's a couple special cases. For a large number of tangents, you pick two of the tangents, turn them into secant squareds, and now you have the secants that you needed to do the thing you wanted to do. I bumped into my volume button, is what it means when it tells me what music I'm listening to. For this thing, you do u equals secant x. It becomes the integral of u du, because du is secant tangent. You get 1/2 u squared, you get 1/2 secant squared x. Minus integral of tangent becomes plus natural log absolute value cosine. I'm writing these sloppy because we've already done these examples or things that are almost exactly similar to them. And also because it's been a long lecture. What else can we do? Here's a very specific trick. When you see a 1 plus cosine x somewhere, here it's in a denominator, which is kind of a painful place. If it was in the numerator, I know how to integrate 1 plus cosine. There's something really special to know about when you see 1 plus cosine, or 1 minus cosine, or 1 plus sine x, or 1 minus sine x. These are kind of special because 1 plus cosine times 1 minus cosine makes 1 minus cosine squared. There's a difference of squares for which this is a factor that you love. I'm going to multiply the top and bottom by the conjugate of the bottom, multiply by 1 minus cosine x, because that gives me 1 minus cosine squared x. And now all of a sudden I don't have two things on bottom. Those magically turn into one thing. This trick is like super niche because it only works if the number is 1. If you have a different number, like you're just out of luck, this trick doesn't work. 1 minus cosine squared is just sine squared. Similarly, 1 minus sine squared is cosine squared. So if you have one of these, maybe add the other one. Is this doable? How do I do this now? We'll probably split it into separate fractions. 1 over sine squared minus cosine over sine squared. Is that hard? 1 over sine is cosecant. Aha! That is the integral of cosecant squared x. That's almost the derivative of something. Derivative of tangent is secant squared. Derivative of cotangent is negative cosecant squared. So this is going to be negative cotangent. How about cosine over sine squared? You can do the substitution u equals sine x, and that'll work because I have the derivative of it right on top. You'll get, 1 over sine. Or, if I split this up into cosine x over sine x, damn it. Times 1 over sine x. Well, that's cotangent x. And that's cosecant x. And hey, I happen to have memorized that that's the derivative of cosecant x. Boom. So, there's a thing to know. The particulars of doing that integral aren't the trick. The trick is when you see 1 plus cosine, 1 minus cosine, especially if it's inside a square root, things get easy. What else do I want to say? Oh yeah, we gotta talk about this. If you have integral of cosine 3x sine 2x, or if they're both cosines, or if they're both sines, there's two ways to do an integral like this. Option 1, is there's a thing called a product to sum formula. It's a giant list of 3 formulas to memorize, and they are the worst. I will write them down, but I don't really recommend that. For me, if you've already got these memorized, hooray for you. If not, you're kind of... it sucks. Sine A cosine... sine times cosine can turn into a sum. Sine A cosine B can be rewritten as 1/2 sine A plus B plus 1/2 sine A minus B. If you foil's not the right word, but if you expand these out with the angle addition formulas for sine, you'll have sine A cosine B, sine B cosine A, and the way these are rigged up, the ones you don't want will cancel out, and you'll just be left with a sine and a cosine. If you have sine, you can do that with cosine. Sine A sine B is 1/2 cosine A minus B plus 1/2 cosine A plus B. If you have cosine A cosine B, that can become 1/2 cosine A plus B plus 1/2 cosine A minus B. I've messed something up. There's supposed to be a minus somewhere. I wouldn't copy these down from my lecture. I would go Google these. It's called product to sum formula. Maybe people have a better way of remembering them. I don't remember these ever because you don't need to, but let's use it once. Cosine sine, according to this formula, I can rewrite this as... let me... red. Let me make that in red because I messed it up the first time. This is sine something cosine something. So according to the first product to sum formula, this is 1/2 of sine of 3x plus 2x, that's 5x, plus 1/2 sine of 3x minus 2x, that's just x. And this is integrable. Negative 1/10 cosine 5x. Integral of sine is negative 1/2 cosine x. Done. Not too bad. But if you want to use that formula, you got to memorize that formula, and I don't want to memorize that formula. So a worse way of integrating it with less memorizing is valuable to me. The other way to integrate this is to do parts twice. I won't write it out because we've done enough parts already today. But the idea is if I make u be my cosine 3x and dv be my sine 2x, I'm going to turn it into a sine 3x and then a cosine 2x. Do parts again, the sine will turn back into a cosine 3x. The cosine 2x will turn back into a sine 2x. I'll have the original integral again, move it to the other side, divide by something. It's that trick. Taking the derivative of this twice turns the cosine back into a cosine. Integrating this twice turns the sine back into a sine. Once you have the original integral again, you can do it. That's trig tricks. Am I done lecturing? Do I have a problem I want to do? Sine squared, secant cubed. We did something like that. We did something like that. Man, this... Sorry about my stylus. I'm going to Google what to do about my stylus. Someone's got to have figured this out by now. Yep. Okay, I'm going to stop talking for today. We covered a lot of stuff. Take a look at the homework. You should be able to do everything through trig tricks. Went up until number 23. Try out number 1 through 23. I'm probably going to... I need to add some of those where you need to use that double angle formula. Is there really nothing like that in there? Oh, there's... No. There's all sorts of extra stuff going in. A lot of these need a substitution, and the lecture is mostly focused on the trig part, not the substitutions that are related. Try these problems out. If you have questions, stick them in the group texts, or you can text me privately, and I'll either get back to you or we can do them at the start of class next time. See you tomorrow. end stream.